An Airbus A321 is cruising smoothly across the European skies in what looks like a completely normal way. But inside, its pilots are working frantically to try and keep the aircraft's nose above the horizon, as the very system that was supposed to keep them safe is now fighting against them. If you regularly watch my channel, you might be familiar with the stories of the two Boeing 737 MAX crashes which occurred in late 2018 and early 2019. In both those cases, a jammed angle of attack sensor incorrectly activated a newly fitted protection system, which ultimately drove both those aircraft into the ground. And you probably thought that this is a problem completely unique to the 737 MAX. Well, as it turns out, that's actually not entirely true, as the two Lufthansa pilots in this story were soon about to discover, almost 4 years before the first MAX accident happened. On the 4th of November, 2014, what would become the incident aircraft, registered as Delta Alpha India Delta Papa, landed normally in Bilbao, Spain, and was then left overnight before its planned return flight toward Munich the following morning. Now, there had been no technical issues on the inbound flight, nor anything else worthy of reporting. So, when the Lufthansa crew that was supposed to do the morning flight returned to the airport, nothing in their briefing material suggested that this flight would be any different. The weather was cloudy with some moderate icing forecasted between 10,000 and 17,000 feet, and there were also some very strong winds at altitude, which could cause turbulence at times. But beyond that, everything was looking standard for this late autumn day. So, the captain briefed the 4 cabin crew members accordingly, and together with his first officer, they then walked out toward the aircraft and started preparing it for departure. The captain was 52 years old at the time and was very experienced. He'd been flying commercially since 1988 and had accrued a total experience of an impressive 16,438 hours, of which the vast majority, just under 12,500 hours, had been flown on Airbus A320 family aircraft. The first officer was 35 years old and had been flying since 2006. And he was at this time also very experienced with 6,473 hours of total time, of which around 5,200 hours have been flown on this aircraft. So, together these two pilots must be considered highly familiar with the type, and that experience would soon be put to the test. As part of the preparation, the two pilots decided that the first officer would be pilot flying for the leg up to Munich, with the captain as pilot monitoring. This meant that the captain soon went outside to do the walk around, where he noticed nothing out of the ordinary. So, when the 103 passengers had boarded, the doors were soon closed, and the gleaming Airbus A321 started taxiing out for departure with a total of 109 souls on board. Now, there were no reported delays during their taxi out. So, at 7:48 local time, the first officer moved the thrust levers into the toga detent, and the aircraft started accelerating down the runway for a completely normal takeoff. They then turned northeast toward French airspace for the planned 2-hour flight. As part of that climb, the aircraft soon entered those dense clouds and started encountering the moderate icing that the forecast had been talking about. But all procedures were followed, and the aircraft's de-icing and probe heating system was indicating that it was working exactly as designed. Something was now silently starting to go wrong, and to understand just how and why it would come to have such a dramatic impact, I now need to go through a fairly thorough technical explanation, as well as some aerodynamics. So, pay attention here, because this is utterly fascinating. As you probably know, all modern Airbus aircraft are controlled via what's known as a fly-by-wire system. This means that the pilot steering inputs are translated by sensors into electrical signals. Those signals are then routed through a computer before being sent out to the hydraulic actuators of the flight control surfaces. That's why it's called fly-by-wire, because the pilot's inputs are transferred electronically through wires rather than mechanically via cables, pulleys, and push rods. Now, fly-by-wire is not a new technology. The military has been using it since at least 1957, and the first civil airliner to be equipped with it was actually Concorde in 1969. Given the computing power available today, fly-by-wire is no longer an exotic way to control an aircraft. Essentially, it enables clunky hardware like control rods, pulleys, and cables to be removed, thereby saving a lot of weight. And the beauty of it is that it also allows for great freedom in aircraft design and control. Actually, to fully illustrate what fly-by-wire technology can do, consider the B-2 flying wing bomber. In order to keep it as stealth as possible, it has no vertical fin, and this makes it inherently unstable, which means that without hundreds of micro-adjustments made by its quad-redundant fly-by-wire system every second, it would be completely uncontrollable for a human pilot. But as it turns out, this instability is not even noticed by the crew. In fact, pilots who have flown it say that the B-2 is remarkably easy to fly and that the aircraft responds smoothly to even small inputs. Characteristics which are an illusion created entirely by that fly-by-wire computer system. Now, of course, commercial transport aircraft who use fly-by-wire systems are not inherently unstable. For example, even if the flight control computers on an Airbus A320 would fail, a backup mode still allows the aircraft to be fully controllable. When the A320 was introduced back in 1988, it was the world's first digital fly-by-wire commercial aircraft and the first featuring a side stick. So, you might therefore assume that fly-by-wire and side sticks always go together. But this is not necessarily the case. In fact, the Boeing 777 and the 787 have conventional control yokes, but are also equipped with a fully digital fly-by-wire system. And while this might suggest that there's little difference between Airbus and Boeing designs, I assure you, there definitely is. And one of the key differences is aerodynamic feedback, or rather the lack of it in Airbus side sticks. I'll get back to that in a moment, because this is a thing that I am personally quite fascinated by, and I think most people don't really fully understand. And where were we? Yes, feedback. Now, let me explain why feedback is normally so important. At high speeds, the controls of a conventional aircraft will feel heavier than at low speeds, where they feel kind of soft and can be moved quite easily. This is a super important parameter for us pilots. In fact, it is so important that an artificial feel system has been designed into the flight controls of conventional jets with powerful hydraulic systems. You see, with 3,000 psi of hydraulic pressure moving the aerodynamic surfaces, there would be no natural feedback from the air loads. The hydraulics are just too powerful. So, instead, this feedback is fabricated by the help of artificial feel units that use springs or hydraulically powered mechanisms to make the controls feel different or lighter, depending on which airspeed the aircraft is flying. And that is really important since a sudden rough control input at high speed could lead to a severe maneuver that could overload the airframe and be super dangerous for everyone on board. Well, let me give you another example, actually. Imagine driving a modern car with power steering on the motorway. At high speeds, the steering is designed to feel heavier, whilst when parking, it feels light, making maneuvering in tight spaces quite easy. That, more or less, is the kind of feedback that a pilot gets from the artificial feel mechanism as well. Now, replace the steering wheel in your car with a control stick similar to those found in gaming consoles. It would have a centering spring and be just as easy to handle at high speed on the motorway as it is when driving slowly. This would obviously make it very comfortable when squeezing into a tight parking space. But if you're hit by a gust of wind on the motorway at high speed, it would require you to only make a tiny adjustment with surgical precision. Otherwise, you could easily lose control and start zigzagging wildly. And that means that this basically would require the hand-eye coordination of a carrier pilot, which would not be ideal for your daily commute, right? Nevertheless, this side stick was precisely what Airbus installed in the first Airbus A320 almost 40 years ago and has then continued to install in all subsequent aircraft. So how does that work then? Well, the answer lies in the freedom that fly-by-wire technology provides. The movements made on the side stick are first interpreted by the flight control computers according to certain rules coded into their software before being transmitted to the control surfaces. And this means that the same input on the side stick results in different amounts and rates of control surface deflection depending on the airspeed, which effectively removes the need for artificial feel. You with me? The aircraft computers will basically make sure that the aircraft reacts like the pilot intends, no matter what the airspeed is. Like I mentioned earlier, when the Airbus A320 was launched in 1988, this design was considered revolutionary. And so many people were impressed by the futuristic look of the cockpit with an empty space and a nice little table with a cloth on it, where the control column and yoke had been, as well as by the fact that it seemed to be almost entirely computer-controlled, that they missed another revolutionary element. A concept called flight path stability. Now, this was also something that had never been used before in commercial aircraft. And the path that Airbus chose with this design would ultimately lead to the story that I'm about to tell you. So what is that then? Well, a flight control system based on flight path stability is designed to maintain a 1G flight path. 1G is the so-called gravitational acceleration. So, if you're sitting in an aircraft during smooth level flight and you don't sense any movement, well, then that indicates that you're on a 1G flight path. If the pilots then want to climb, for example, they will pull back on the side stick. The computer will analyze the input and translate it into movement of the elevators and horizontal stabilizer, introducing a small amount of positive vertical acceleration and diverting from 1G. This is called increasing the G load, and it will last as long as the stick is being pulled back. The aircraft will then be pitched up slightly. The auto thrust system will increase the thrust, and you might experience a slight vertical acceleration. But as soon as the pilot releases the stick, the aircraft will return to its 1G flight path. Only this time it will be climbing. Now, to stop the climb and return to level flight, the pilot will have to push the side stick forward. And that again introduces a small amount of negative acceleration and causes the auto thrust system to reduce power, resulting in the aircraft leveling off. Releasing the stick again resumes the 1G flight path in level flight, according to the fly-by-wire control law that Airbus calls normal law. So, basically, what the side stick would be doing is telling the computers to accelerate the aircraft in a particular direction, and releasing it will maintain that new direction. Point and fly. Now, while this might not sound significant, this method of control is fundamentally different from that of normal conventional aircraft. Those are typically speed stable rather than flight path stable. And that means that the aircraft wants to maintain the speed that has been trimmed to. That speed depends on the position of the horizontal stabilizer, which is movable and found on most commercial jets. And the pilot can adjust it using the trim switches, moving it either up or down. The resulting position of the stabilizer essentially determines the speed which the aircraft will fly if the pilot releases the controls with the elevator in its neutral position. So, when you're flying a conventional speed-stable aircraft trimmed for a certain speed with a power setting that maintains level flight, if you pull the control yoke back without increasing thrust, the nose will come up and the aircraft will start to climb, causing it to lose more and more speed. And the moment you remove your hand from the controls or release your pull, the nose will start coming back down. The aircraft will descend and try to return to its trimmed speed and eventually level off close to the altitude you had before. Therefore, if the pilot doesn't actively continue to pull back, the aircraft will not normally stall, just because the pilot pulled on the yoke once. In other words, in order to force the aircraft to climb without increasing thrust, the pilot must either pull harder or use the trim switch on the yoke to adjust stabilizer to a slower speed. Only then would the control forces stay the same instead of increasing, and the aircraft are constructed like that exactly to discourage a pilot from forcing the aircraft into a stall unintentionally. Ultimately, though, if the pilots keep pulling back without adding thrust, the speed will continue to fall. The stick shaker will be triggered at some point together with other warnings of an impending stall, and in some designs, this is even done followed by a stick pusher that actively brings the nose down. But the really crucial point here is that it is up to the pilots if this will happen. They can bring the aircraft into a stall if they would like to. So instead of taking the pilot completely out of the loop, the conventional system only discouraged them from certain maneuvers. Now, this safety characteristic obviously doesn't require a fly-by-wire system, since it's an aerodynamic feature, and it was therefore already in place on early jets like the Boeing 737 and the 727, for example. But let's now pull a flight path stable aircraft with a feel-less spring-loaded side, stick into a climb without increasing the thrust. With your input, you will now command a climbing flight path regardless of airspeed. And ultimately, underneath the flight path stability, there still sits a speed-stable aircraft, which also has to be trimmed. But in the Airbus, this will be done automatically. So if you release the stick, the nose will not drop. Instead, the aircraft will just continue to climb. There are actually trim wheels on an Airbus A320 as well, but they move by themselves as you can't override the auto trim while it's in normal control law. So if you do not increase your thrust, you could in theory fly the aircraft straight into a stall with the help of the auto trim function. In reality, though, there exists a system of protections that were built into the system to prevent exactly that from happening. But unlike Boeing, Airbus decided to use so-called hard protections, which the pilots cannot overrule. So here we come to a fork in the road called the control philosophy of modern commercial jet aircraft. Boeing helps the pilots to stay within the aircraft's limits, while ultimately still granting them the privilege of final decision, even on their fly-by-wire aircraft. But Airbus, on the other hand, keeps the pilots away from those limits by taking that privilege away. You see, Airbus engineers dreamed of building an aircraft that pilots couldn't overbank, overspeed, or stall, no matter how much they tried. And to achieve this, they designed these hard limits into the flight control software. Basically, to try and build an unsinkable aircraft, which is where spring-loaded side sticks, flight path stability, and hard protections all kind of come together. Now, while it was comparatively easy to prevent overspeeding or overbanking, preventing a stall turned out to be a completely different story. So, it was here that the Airbus engineers presented their piece de resistance, the high angle of attack protection system. This is the most complex protection system that Airbus engineers have ever designed, and it supposedly makes the aircraft impossible to stall under normal circumstances. Now, in order to build an aircraft that is impossible to stall, it is necessary to prevent it from exceeding its maximum angle of attack in any flight situation. So, we now need to know what that is. The angle of attack, also known as AOA, or simply alpha, refers to the angle between the wing's chord line and the direction of the air impacting the leading edge of the wing. Basically, it's a measure of how much a wing is tilted into the airflow, and if that angle increases, lift and drag will continue to build up until the wing reaches an angle that Airbus calls alpha max. There, the wings are producing maximum lift, and beyond this, the air flowing over the top of the wing will not have enough energy to continue following the curved surface, and that will result in the airflow breaking away and becoming turbulent. The angle where that happens is called the stall angle of attack, and while it is more or less constant in light aircraft, it is variable in jets because they fly at much higher speeds and at higher altitudes where the air is much cooler. Now, for a clean wing without slats or flaps, the stall angle of attack, especially at higher altitudes, depends primarily on the aircraft's speed relative to the speed of sound or its Mach number. For example, Mach 0.8 means 80% of the speed of sound, and as the Mach number increases, as it does when it gets colder outside since it's inversely correlated with temperature, the angle of attack at which the wing will actually stall decreases significantly. So, as a rule of thumb, during a climb, the stall angle of attack will get smaller and smaller the higher you climb as it gets colder with altitude, and the Mach number therefore increases. Remember that. Now, remember how we climbed the flight path stable aircraft with its engines at idle by pulling the nose up, thereby increasing the angle of attack? Well, as the nose rises, the airspeed will drop and the aircraft will lose energy. So without protection, it would eventually stall. But in an Airbus at a certain angle of attack, which Airbus calls alpha prot or protection, which is close to alpha max, the flight control computers will suddenly change the control law in the pitch axis. Now, this is important because if the pilots would now move the side stick, they will no longer control the flight path, but instead the angle of attack. If no inputs are made, or if the stick is released, the aircraft will just remain at the angle corresponding to alpha prot, which is still a safe distance away from alpha max, regardless of whether this results in a climb or descent, which is actually also worth remembering here. But on top of this, if the speed is below a certain threshold, the auto thrust system will also engage, increasing the engine thrust up to maximum. Airbus calls this the alpha floor mode, and if the pilots would still continue pulling on the side stick until max, well, then the control law will allow the angle of attack to increase up to alpha max, but not further than that. Remember, that's the angle of attack where the maximum possible lift is being generated. What this all means is that with the thrust levers at their forward mechanical stop and the side stick at its aft mechanical stop, the normal control law will provide the maximum lift that the aircraft can possibly generate without ever stalling. Now, this is a really smart protection system for several different reasons. Not only does it prevent the pilot from stalling the aircraft inadvertently, it also enables them to access the aircraft's maximum lift capability whenever necessary without requiring much thinking or handling at all. In a wind shear scenario, for example, when the aircraft flies through a severe downdraft, the thrust levers must be pushed fully forward, and then the aircraft must be flown with an angle of attack close to the stall angle of attack, since this is where maximum lift is generated. In a conventional aircraft, like the Boeing 737 that I fly, you would need to follow the horizontal bar of the flight director carefully, making precise control inputs, and taking care not to stall the aircraft. And in an Airbus, you would initially do the same thing, but if that's not enough, all you need to really do is then to pull the side stick aft stop, making sure you have full thrust. The high angle of attack protection will then ensure that the maximum lift is obtained from the wings without ever stalling it. So, the following story that I'm about to tell you now is not intended to diminish how great this system really is, but the fact is that we also live in the real world where blessings sometimes have side effects. So, now that you hopefully understand all of the intricacies with this system, let's get back to the flight. As Lufthansa Flight 1829 approached about the 30,000 feet, the air traffic controllers cleared it to turn towards a waypoint called LATEC. But when the autopilot initiated that turn, the captain suddenly noticed something unusual on the speed scale of his primary flight display. You see, at the bottom of the speed scale, there is a red strip marking the speed corresponding to the maximum angle of attack. And this is then followed by a black and amber strip marking the alpha protection speed. Remember, that was the speed at which the pitch component of a normal law would change, and the side stick would start commanding angle of attack instead of 1G flight paths. Finally, the amber strip at the top marks VLS, which is the lowest selectable speed or the minimum speed that the aircraft can be commanded to fly in a normal situation. Now, during flight, it is normal for the black and amber alpha prot strip to move up and down on the speed scale, since a change in the amount of lift required also changes the angle of attack. So, when Lufthansa 1829 turned towards LATEC at the time 8:03, some movement was to be expected since the wings have to provide a little bit more lift during a turn, but the captain now saw an unusually large rise of the strip, bringing it uncomfortably close to the aircraft's actual speed. The first officer was flying the aircraft also saw the same, and therefore now reduced the vertical speed to about 500 feet per minute, hoping that by doing this, it would cause the aircraft to accelerate a little bit and move away from the alpha prot. But when that didn't work, he instead disconnected the autopilot and moved his side stick gently forward to manually lower the nose. And to his horror and surprise, this resulted in the aircraft now pitching forward violently. He immediately tried to counter this by pulling the side stick back to about 3/4 of its travel, but the nose-down attitude just kept increasing to -3½ degrees, causing a sink rate of close to 4,000 feet per minute, which is actually not far away from the rate that you would expect during an emergency descent. After 45 seconds of trying to fight this mysterious pitch down, the first officer finally told the captain that he was unable to stop the descent, and the captain therefore took control of the aircraft. He now pulled his side stick aft to its mechanical stop, and as he did that, he was finally able to arrest the descent rate, and the aircraft leveled off at around 27,000 feet, but this situation was still far from over. The captain still now had to pull his side stick back to about 50% of its full travel in order to just maintain level flight. The autopilot could not be engaged, and the automatic pitch trim didn't work either. So, this aircraft was now barely in control, and there was no indication of why this was happening. So, the pilots started consulting their quick reference handbooks to verify that their pitch and power values corresponded to the airspeed indicated on the primary flight displays, because they thought that maybe they were facing some kind of unreliable airspeed situation. But when they checked it against the tables, their indicated values ended up matching with what the QRH said that they should have. So, they quickly ruled out the indicated speed as a problem. And since there was now no other warnings to guide them, they had to accept that the QRH would be of no further help. This was something new and something that wasn't that easy to figure out. So, the next thing that they did was to reset the two flight augmentation computers, or FACs, which forms part of the fly-by-wire system, hoping that this would reset whatever was going on. But it did nothing. At time 8:11 and 12 seconds, 8 minutes after their turn towards Ladakh, the aircraft's ACARS system sent out an automated data link message to Lufthansa's maintenance department. It contained various parameters, including the angle of attack values used by the three ADRs, or air data computers. And about 13 minutes later, about a full 21 minutes into this ordeal, the pilots then wrote a data link telex to the same maintenance department. In it, they described their situation of having to fly the aircraft manually with constant backstick input to maintain level flight, as well as the abnormal behavior of the Alpha Prot strip, which would rise rapidly upon any vertical acceleration. Now, before sending that telex, they had also accessed the aircraft's centralized fault display system, the CFDS, which is actually more of a maintenance task than something that a pilot would be expected to do. In there, they had found a fault message concerning angle of attack sensor number 3, which is one of the 3 sensors that measures the aircraft's angle of attack and is connected to the respective air data reference units. Now, as a result of that information, the maintenance technicians now suggested switching off ADR number 3, which the pilots also did. But when they did that, that also had no effect at all. So they just ended up switching it back on again. By this time, more than half an hour had passed, and the captain was still maintaining the aircraft's altitude by applying considerable back pressure on his side stick. And if he would let that go, the aircraft would just lurch forward into another rapid descent. So, this was obviously not viable for a safe approach and landing. Meanwhile, down on the ground, the technicians had reviewed the automated telex sent out by the aircraft, which contained the angle of attack values of the 3 angle of attack sensing vanes. And based on that, they had now started developing a theory. They told the crew that they suspected that 2 of the angle of attack sensors had frozen, and that they were now transmitting erroneous data to their respective ADR units. So, based on this, they suggested that the pilots should switch off ADR-1 and ADR-2. But a few minutes later, they added that switching off only ADR-2 might do the trick. So, at time 8:59, after almost an hour of flying on the edge of controllability, the pilots did what they were advised to do and switched off ADR-2. And the aircraft immediately returned to normal flying conditions. No more continuous backstick input was needed, and even the autopilot became available again. Now, after a discussion, the pilots decided to continue the flight towards Munich and use the remaining flight time to assess the functionality of all of the relevant systems. And at time 9:49, Flight 1829 eventually landed safely at Munich Airport, where a team of maintenance technicians were now eagerly waiting. But wait, this story is far from over. The ACARS telex exchange between the crew and the maintenance department had already caused quite a stir, even while the aircraft was still airborne. Because of this, as soon as the Airbus A321 had taxied into its gate, it was grounded for 3 days, while Germany's Accident Investigation Authority, the BFU, conducted an extensive investigation in close cooperation with both Airbus and Lufthansa. And what they found was fascinating. About 8 minutes after takeoff, as the aircraft was climbing through flight level 195, with an outside air temperature of minus 35 degrees Celsius, the 2 left-hand angle of attack sensors froze at almost identical values, indicating a median angle of attack of 4.5 degrees nose up. Now, at that altitude, that angle of attack wasn't really a problem, so everything seemed normal. But as the aircraft continued to climb and the outside air temperature decreased, well, then the Mach number steadily increased as well. Remember, the colder it gets, the higher the Mach number will be, and with it, the maximum angle of attack decreased. So, by the time the aircraft reached flight level 300, it was indicating Mach 0.675, and the maximum allowable angle of attack had decreased to only 5.8 degrees. This meant that there was now only a margin of 1.3 degrees between the incorrectly sensed angle of attack of 4.5 degrees and the maximum allowable value. But the high angle of attack protection was designed to activate at a margin of 1.6 degrees, meaning the apparent angle of attack was now already 0.3 degrees higher than that, when the first officer decided to disengage the autopilot. Now, if he hadn't done that, the autopilot would have disconnected itself just a moment later anyway, since the protection was now just about to activate. Now, remember that the protection was designed to maintain the alpha protection angle of attack, no matter if that caused a climb or descent. Well, this is why the flight control law changed from flight path control to angle of attack control when that limit value was exceeded. And when the autopilot in this case was now disengaged, the protection started aiming for the alpha protection angle of attack, which at that altitude was 0.3 degrees below that measured by sensor 1 and 2 on the left-hand side. So, consequently, the system now applied an additional nose-down input to reach that value on top of the input that the first officer was already making. But since the sensors were still frozen, the apparent angle of attack didn't decrease as the nose was lowered at SO. The protection's nose-down inputs therefore kept piling up until the aircraft appeared to be in an uncontrollable descent. Now, if you're familiar with the story of the 737 MAX accidents, you might recognize this scenario. And while there are some basic similarities here, this is still a very different STO. But you might ask yourself, what happened to sensor number 3 then? The one that hadn't frozen up and was therefore measuring the correct angle of attack. Almost all redundant systems in which more than 2 sensors measure the same parameters have a built-in voting algorithm that compares all of the values and then rejects an outlier if the other 2 agrees. So, this was now exactly what happened here. The correct sensor 3 was identified as faulty since the 2 frozen ones agreed, and it was therefore ignored by the flight control computers. And that, by the way, was also why it had been displayed as faulty in the centralized fault display system when the pilots pulled it up. So, with the protection now chasing an angle of attack that couldn't be reached regardless of the pilot's inputs, what was it then that ultimately stopped the descent? Well, remember when I told you that the Mach numbers depend on temperature? This meant that as the aircraft descended, the temperature increased, causing the Mach number to also decrease. And this then raised the ceiling of the maximum allowable angle of attack, increasing the margin between it and the apparent angle of attack. And that in turn reduced the protection system's nose-down vigor and gradually conceded more nose-up authority to the captain's side stick. So, that was what had finally led him to be able to level off at flight level 270, albeit while still needing around 50% nose-up stick input. Now, maybe some of you think that the pilots could have noticed the connection between lower altitude and a higher maximum angle of attack, and simply continue to descend until the protection would no longer have been a factor. But as you probably know, that would be a typical example of hindsight bias and would imply an unrealistic and frankly quite risky scenario. You see, at the time that this happened, this crew had no way of knowing what was causing the uncommanded descent, and they were obviously completely focused on trying to stop it. So, after fighting a protection system that had turned against them for almost an hour, they switched off ADR-2 as suggested by maintenance, and with ADR-3 already rejected by the system and ADR-2 switched off, the Airbus A321's fly-by-wire system now only had one ADR left. And in such a case, it was designed to revert from its fully protected normal law back to alternate law, which still retained flight path stability and similar handling qualities, but without any hard protections. So, that was what ultimately saved the day here, because from then on, the aircraft reacted normally to the pilot's control inputs. And those of you who have watched my video about Air France 447 might remember that the alternate law and the loss of protections associated with it also played a key role there, albeit in quite the opposite way. So, Although this mystery seemed to have been solved here, the most important question still remained. How could two angle of attack sensors have frozen simultaneously at the same values? Well, to answer that, let me first give you a brief explanation of how these sensors work. On the Airbus A320 series, the angle of attack is measured by three so-called alpha vanes. An alpha vane is a small, freely pivoting blade, roughly the size of a finger, mounted on the side of the aircraft's nose. Like tiny weather vanes, they swing to line themselves up with the air streaming past the aircraft, and there they're one on the right-hand side of the aircraft and two on the left. Now, the angle at which these blades settles relative to the chord line of the wing is then sent to their respective air data computers. And those computers then passes that information onto the flight control computers, which calculates the maximum allowable angle of attack. Now, all of Delta Alpha India Delta Papa's alpha vanes were of course removed from the aircraft and sent to the manufacturer in the US, where they were disassembled and inspected under the watchful eyes of B.